So notice that if the matrix A is similar to a diagonal matrix D, then once again there exists an invertible matrix P such that D is the product P inverse times A times P. And so we have that P inverse times the matrix A, B divided by 2, B divided by 2C times P is the diagonal matrix A prime 0, 0, C prime. That is, the cross terms, or the cross term, has been eliminated. So P and P inverse act to translate A to a new coordinate system where the cross terms are eliminated to 0, and only, so it's the coefficients of the cross terms, and only the coefficients of the square terms remain. And so the equation ax squared plus b times x times y plus c times y squared plus f times x plus g times y plus h is equal to 0 is transformed to a new equation, a prime times x prime squared plus c prime times y prime squared plus some multiple of x prime plus some multiple of y prime plus h is equal to 0. But it is the square terms, the remaining square terms, that tell us the type of conic from that equation. If a prime and c prime have the same sign, then we have a possibly degenerate ellipse if a prime and c prime have opposite signs, then we have a possibly degenerate hyperbola. And if either, but not both, of a prime or c prime is 0, then we have a possibly degenerate parabola. So how do we know whether or not this symmetric matrix is diagonalizable, and how can we find the wonderful invertible matrix P that allows us to diagonalize that matrix? And to answer that question, we are going to borrow two theorems, two established theorems from linear algebra. And by borrow, I mean we're going to state them but not prove them here. And the first of those is known as the spectral theorem. And I'll state this simply, that every real symmetric matrix is diagonalizable. And since the symmetric matrix A in the quadratic form is composed of real numbers, it is a real symmetric matrix, and so it is indeed, by the spectral theorem, diagonalizable. So the next theorem that we will borrow from linear algebra is known as the diagonalization theorem. And this theorem states that an n by n matrix A is diagonalizable if and only if that matrix A has n independent, linearly independent, eigenvectors, and in fact, the matrix A is equal to the matrix P times the matrix D times the inverse of P, if and only if the columns of the matrix P are n linearly independent eigenvectors, and in this case, the elements of the diagonal matrix D are the eigenvalues corresponding respectively to the eigenvectors in the matrix P. So let's now use these two theorems. But first, we'll prove a classification theorem. A non-degenerate conic, which we'll call E, with equation ax squared plus b times x times y plus cy squared plus plus f times x plus g times y plus h is equal to 0, and quadratic form, X transpose times the vector, the matrix A times X can be classified as follows. If the determinant of A is positive, then the conic E is an ellipse. If the determinant of A is negative, then the conic E is a hyperbola. And if the determinant of A is equal to 0, then the conic E is a parabola. So proof. By the spectral theorem, we know that the matrix A in the quadratic form, which that matrix A is a real symmetric matrix, and is therefore diagonalizable. And so A is similar to the to a diagonal matrix D. Have that A, which is the matrix A, B divided by 2, B divided by 2, C, is similar to the diagonal matrix D, which by the diagonalization theorem contains eigenvalues on its main diagonal. And so I'll represent those as lambda 1 and lambda 2. And so the determinant of A is equal to the determinant of D, since these two matrices are similar, and the determinant of D is the product, lambda 1 times lambda 2. Now, if lambda 1 times lambda 2 is positive, then lambda 1 and lambda 2 have the same sign, and so the conic E has a transformed equation of the form lambda 1 times x prime squared plus lambda 2 times y prime squared plus some coefficient f of x prime plus some coefficient g of y prime plus h is equal to 0. And since, again, lambda 1 and lambda 2 have the same sign, this is an ellipse. Now, if lambda 1 times lambda 2 is negative, then lambda 1 and lambda 2 have opposite signs. And so again, the conic E has a transformed equation. That is an equation in a different coordinate system of the same form, lambda 1 times x prime squared plus lambda 2 times y prime squared plus some coefficient times x prime plus some coefficient times y prime plus h is equal to 0. But here, lambda 1 and lambda 2 have opposite signs, and so this is a hyperbola. And if lambda 1 times lambda 2 is equal to 0, then either lambda 1 is 0 or lambda 2 is 0, but not both. So without loss of generality, we may assume that lambda 1 is 0. And so the conic E has transformed equation, has the transformed equation. Lambda 2 times y prime squared plus some coefficient times x prime plus some coefficient times y prime plus h is equal to 0. And this is the equation for a parabola. So let's look at an example. We will show that the equation 3x squared minus 10 times x times y plus 3y squared plus 14x minus 2y plus 3 is equal to 0 is a hyperbola. So the quadratic form for this equation is x transpose times the matrix 3, negative 5, negative 5, 3 times the vector x, and the determinant of this matrix, 3, negative 5, negative 5, 3, is 9 minus 25, which is negative. And so this conic, this equation, which I'll call star, is a hyperbola. So as an exercise, write the matrix form which again is x transpose times A times x transpose plus J transpose times x plus H is equal to 0, and calculate or find the determinant of the matrix A for each of the following. The equation x squared plus y squared is equal to 0. The equation x squared minus 2 times x times y plus y squared is equal to 0. And the equation y squared minus x squared is equal to 0. Okay, so we'll end here for now. Next time, we will develop a test to determine whether or not a given general equation represents a degenerate conic, and then we'll move on to quadratic surfaces. So I hope you have enjoyed the 5th lecture. Thanks for watching.